Okay, let's go ahead and get started. We are looking at Unit 1, Lesson 2, factoring, some factoring basics. So, Mrs. Contreras, what does the word factoring mean to you?
Factoring, I think, well, it's like looking at parts of things so that when you combine them in some way that it makes something else.
So would you consider, if I have the number 5, I'm going to write it here on the side, because what we're concerned about now is factoring the number 98, specifically the term prime factorization. If I have the number 5, if I look at its components, 3 plus 2, have I factored the number 5?
No, you have broken it into components, but it's not, but the operation you're using is addition, not multiplication. So I guess we should revise our understanding of factor to also include that we're specifically looking at multiplication.
Yes. So we want, when I ask you to factor things, we're going to take objects. Sometimes it'll be just straight up numbers. Sometimes it'll be expressions, and we want to decompose it into the product of smaller things. So can you think of a way, 2 numbers that are smaller than 5 that multiply to 5?
Strictly smaller than 5?
Strictly smaller, yes.
Not whole numbers.
Okay. So when that happens, we call this number a prime. A prime number is a number that does not have a factorization of smaller numbers that their product is 5. So we can't decompose this into 2 smaller numbers that are being multiplied to 5. So we call this a prime number. If we can, let's say the number 6. Can I take the product of 2 numbers that are strictly smaller than 6 to get 6?
Yes, 2 times 3.
2 times 3. We have factored 6. We have broken it up into the product of smaller numbers. In this case, numbers. Sometimes, once again, it won't be numbers. It'll be smaller expressions. So 2 times 3. This number is called composite. Right? So I want to do that with this number 98. I want to find out the product of what numbers give me 98. And when I say prime product of numbers, prime factorization, I'm looking for numbers that I cannot continue to break down. So can you give me 2 numbers that multiply to 98?
Well, it's even, so I know that I can do 2 and 49.
2 and 49. And what I'm going to do is I'm actually going to break this up into a tree. That's my preference. You don't have to do that. But I'm going to go ahead and write 2 times
trees.
49. Trees are nice.
Trees are good. My favorite tree right now is birch trees.
I like redwoods. I went to the redwoods last year.
Nice.
In California. All right,
That's where they filmed. That's where they filmed the Endor scenes.
That is true. That's exactly why I went too. We went and found that place. Go Star Wars.
Yeah.
All right. For those who don't know, Mrs. Contreras loves Star Wars. Am I correct?
Pretty big fan.
Pretty big fan. All right. So we got 2 and we got 49. Can I continue to break down 2?
No. 2 is prime.
Cool. How about 49?
It's our smallest prime, right? Because 1 isn't prime.
Yeah. 1 is not prime. One might argue that it is, but we're going to go ahead and just exclude that from all of the whole numbers and just not worry about 1. Start at 2.
1 might argue that it is, but it doesn't get to argue because it's a number. It's 1.
This is going to be fun. I'm already having a great time. I'm glad this is being recorded. All right. Can 49 be broken down?
Yes. 49 is a perfect square. That's 7 times 7.
That is 7 times 7. Sweet. We could do an aside right now about all the perfect squares, but let's save that for another time, unless, of course, you want to. Let's not make the video too long. All right, so we got 2, 7, and 7. I'm going to go ahead and write 98 as the product of these 3 numbers. 2 times 7 times 7. And I have now found the prime factorization of this number. Right? We have 3 numbers that are all prime. They cannot be factored any further. And their product is that number 98. So that's what we mean when we look at the prime factorization of a number. This is unique.
Do you care if we write it as 2 times 7 times 7, or if we're more efficient and we do 2 times 7 squared? Is that allowed too?
So I guess one might argue that, is this more efficient? I've written 1, 2, 3 numbers, and I've written 1, 2, 3 numbers. I don't think it matters. What is your opinion?
I don't know. I think that sometimes I get lazy and I feel like writing smaller numbers rather than writing more.
If we're talking real estate, this does take up less space on the page. All right, so we found this prime factorization. This is unique. No matter how you do this process, you're going to get 1, 2, and 2 sevens. And that's a much more profound question that will be answered hopefully later. But prime factorizations are unique. So to those that are watching this video, you're about to be prompted to find the prime factorization of 2,601. And there are some tricks that you might be able to use, hint, hint. But go ahead and do that, and then you're going to be prompted to choose one of the possible prime factorizations. Good luck. But now that that's over, we're going to go ahead and proceed. All right, the greatest common factor. So notice that this doesn't say prime anymore. We're no longer looking for a prime factor for these numbers. I want you to find the largest number, the greatest number, that goes into both of the numbers presented. So here I have 60, and here I have 156. Do you have any ideas on how to approach this problem?
Well, I think 156 feels like it's something important. Like it would be a way that we can start thinking about it because it's the bigger number, so it would have more factors. But at the same time, that feels like a lot of work. So if we could just look at the different factors of 60 and then eliminate some that aren't common factors with 156, maybe that's a better way.
All right, let's do that. I hear what you're saying. So how do you want to find the factors of 60?
I just want to start with 1 times 60 and then go from there.
Yeah, so I'm going to do a little like chart here. We got 1 and 60.
2 and 30.
2 and 30, even.
3 and 20. 4, no. And
Deceived me.
15. 4 and 15.
Oh, you have not deceived me.
5 and, wow, 60 is such a great number. 5 and 12.
You actually have a name for it. I'll say it in a second. 5 and 12.
6 and 10.
6 and 10. Oh my gosh. Why is this list still going?
7 doesn't work.
And then 8 and 9 also don't work, right? I guess if 7 doesn't work, then like there's no way 8 and 9 will work. Mm-hmm. We call it a highly composite number. Not a very fancy name, but
highly composite.
Yeah. It's one of the reasons why 360 is such an important number to ancient civilizations. It's a highly composite number. A lot of divisors. 1, 2, 3, 4, 5, 6. I think 8, 9, 10, all of those. I think 7 is the only one that doesn't go into 360. Well, whatever. All right, so we have all of these factors. Which is the greatest one that also goes into 156?
It's probably not 1.
Definitely, because 2 definitely goes into both, right?
And it's also probably not 10, because 10 doesn't end in a 0 or a 5. Should we like sandwich, or like how do you think we should attack elimination?
Oh, this is a good point. I don't know. My preference would probably just be elimination if we're using this method. Like 60 won't work, right? 30, will 30 work? No, same reason for 10. 20 won't work. 15 won't work. I know numbers that end in 5 only go into numbers that end in 5 or 0. 12. Does 12 go in?
Does 12 go in? Well, because 156 is almost 144, and I know that's 12 squared, right? So then what's 12 more than 144? 156.
56.
Oh, lovely. So then it would be 13 times 12 is 156.
Boom. Right? None of these go into 156. 12 is the greatest factor that is common between the two. The GCF, the greatest common factor. There is another strategy that we can do to solve this problem. Do you know what it is?
No, I don't think I do.
All right. Let's do what we did in the previous part of this packet, and that was prime factorization. So let's look at the prime factorization. Yeah, let's make some trees. Let's do it with 60, and let's do it with 156. Right? As you get better at this, you can do it really fast. So 60 would be, let's go with 2 and 30, 2 and 15, 3 and 5. Over here, 156. What would be a good one for this? We could do 12 and 13 now that we know that, right? But you could use whatever number you want. Once again, it's going to be unique. No matter what you do, it's going to work. All right. 12 and 13, so we can do 2 and 6, and then 3 and 2, and I don't believe I'm missing anything. By preference, I like to have numbers next to each other. 2, 2, 3, and 13, 2, 2, 2, sorry, 2, 2, 3, and 5. All right.
I like a little bit more chaos in my life, but
yeah,
it's fine.
True.
And if you didn't know that 12 and 13 were factors of 156, then couldn't you just start with, oh, well, this is a even number, so I know that 2 will work, and then I can work from there?
Yeah, and there's another cool trick. If you add up the digits of a number, 1, 5, and 6, you get 12. If that number, 12, is divisible by 3, then the number itself is divisible by 3. And there's a cool reason for that, and we can look at that in a later unit. Let's continue. So we got 2, 2, 3, 5, and 2, and 2, and 3. Right? I'm going to look at what is common between these two prime factorizations. Right? What numbers in these two prime factorizations are common, Ms. Contreras?
Well, it's everything except for 13 and 5. Those are the things that aren't the same. But everything else, 2, 2, and 3, those are all the same.
I'm going to go ahead and circle some stuff. We got 2 and 2. So I'm going to write that down here. We got 2 and 2. Cool. That's another 2. We got a 3. That's another 3. I forgot to circle it. And then the 5 and the 13, they are non-common. Right? So the product of these, 2 times 2 times 3, 2 times 2 is 4, times 3, that is 12, our GCF.
Whoa, mind blown.
The reason why this kind of works is if you imagine 60 as 2 times 2 times 3 times 5, if you take 2, 2, and 3, you're going to get 12 times 5. And over here, if you break this down into its prime factorization, you're going to get 2 times 2 times 3 times 13. That's going to be 12 times 13. So they have that 12 in common. And then these two prime numbers are not contributing anything that's common. So we're going to stop the video probably we're going to stop the video in just a second so you guys can do number 2. We're going to stop it here. All right, let's continue.
We should have like a little thing that we hold up.
Yeah, we should probably also say the answer, which I don't actually know the answer. I think I need to do it to know the answer.
Is it 9? I feel like it's 9. Wait, 108.
For a future video, we'll be a little bit more prepared. Sorry, Precalculus. All right, let's continue.
We still love you, though.
Yeah. Factoring out the greatest common factor. So we got number 1 here, 2x minus 6. We have 2 terms. I like to think about terms as expressions within an expression that are separated by addition. And minus subtraction is really just addition of a negative number. So we have this addition symbol here. So the terms are separated by that. So 2x is a term and 6 is a term. So we're looking at those 2 terms. What is the greatest common factor of those 2 terms?
I think 2.
Yeah, 2. And so we can take that 2 out. And what I want to do, I call this using the reverse distributive property. Let's see if I can spell distributive right. You guys will learn that I am not good at spelling.
We became math teachers for a reason.
All right, so we got 2x minus 6. I want to do reverse distribution. So I write the 2 out here because we've established that that's the greatest common factor. What times 2 gives me x?
X.
Sorry, what times 2 gives me 2x, and you're correct, x. And then what times 2 gives me a negative 6?
Negative 3.
Negative 3. Wonderful. So we've done the process of factoring out a greatest common factor. This one's a little bit more difficult because we got a little bit more going on. We have 3 terms, but the greatest common factor process works exactly the same. What is the greatest number that goes into those 3? We'll give you guys the chance to solve this one here. Let us know what you get. Cool. Let's go ahead and proceed. All right. Factor by grouping. So if you guys haven't noticed, this introduction lesson is all about factoring. We want to factor this expression. What does that mean? It means that we want to decompose this into the product of different things, of different smaller expressions. So do you have any suggestions here, Mrs. Contreras, to attack this problem? We're going to factor by grouping.
It says grouping, so I feel like we should group things and then maybe try that reverse distribution.
Okay, let's do it.
And see what we get.
Okay.
We might need to do that twice.
I'm going to let you pick. How do you want to group these? I see 4 terms, 2x cubed, negative 6x squared, 5x, and negative 15. How do you want to group them?
I think I want to group the first 2 terms together because I can see that there is pretty nice common factors with those. And then I want to group the second 2 terms together.
All right, I'm going to use parentheses to visually describe that I'm grouping. Cool. And my handwriting got a little bit sloppy there at the end. I do apologize. All right, so let's do exactly what you said. Reverse distribute. Distribute. I'm going to say that word wrong a lot. What is the GCF between these 2 terms?
I think 2x squared.
Yeah, 2x squared goes into that one. And then 2x squared times what gives me 2x cubed?
I think that's an x.
Yep.
And then a minus 3.
Yep. All right, how about over here?
I think it looks like 5 is the only thing we can take out.
Let's go ahead and take it out.
Reverse distribute, excuse me. And then we get x minus 3, which is lovely because that looks like it's the same for the first and the second.
So I will say that factor by grouping doesn't always work, but it has worked here because we have been left with an identical term in both of these 2 products. And we have this x minus 3 here. This expression is appearing twice. That expression is a factor. So what is the greatest common factor between, let me get some colors going, this and this?
X minus 3.
X minus 3. So let's go ahead and take it out. X minus 3 times what gives me this entire expression?
2x squared.
Yep. And then x minus 3 times what gives me this entire expression?
Just a 5. Positive 5.
Positive 5, yeah. And that positive does matter. Especially when it's negative. The negative will matter. All right, there we go. We factored x minus 3. We factored that. And then this does not look like it's factorable. And if you don't see why immediately, just hold out for a little bit, and then we will see why that's not factorable later. But for example, we don't have any GCFs when it comes to the numbers. And we don't have any GCFs when it comes to the variables, x squared. So we're going to leave that how it is. Cool. All right, we got this problem right here. We're going to give you a chance to do it. And we are going to move on. All right, we want to build up to factoring quadratics. A quadratic is an expression that has a quadratic term, x squared. All right, the leading term, the term with the largest exponent, is a square. That's what a quadratic is. So to do that, let's look at something that's already been factored, this, expand it, and see if we can establish any patterns. You may have done this before in a previous class, but this will lead up to something that's a little bit more difficult. And we want to do it with a simple thing so that the more difficult one is more obtainable. So let's go ahead and expand this. Mrs. Contreras, I hear you have strong opinions about vocabulary here.
Well, expand that's a good way of putting it. I think there are people who choose to refer to this as called foiling. And foiling is very effective when you're multiplying 2 binomials. 2 binomials meaning two terms that both have only the things you're multiplying only have 2 terms each. So foiling is only good for 2 binomials. If you suddenly throw in a trinomial into the mix, FOIL no longer works. So the more generalizable way of expressing yourself and sounding educated, because you are educated, is I would like for you to call it using the distributive property. But if you slip up and you call it FOIL, I will not be that upset, but I might laugh at you under my hand.
So if you ever see Mrs. Contreras' hand go here, she's probably laughing at you. All right, so let's do it. Let's use the distributive property. So let's distribute this x plus 5 to the x and to the 6, like we did in the previous example. That was reversed, though. We're going to do it the correct direction. Correct the wrong word. In this direction.
In this direction.
X plus 5 times x, that's just going to be x times x plus 5. And x plus 5 times positive 6, that's just going to be positive 6 times x plus 5. I think I didn't mess anything up. Cool. All right, we'll do the distributive property again. X distributed to x is x squared. X distributed to 5 is 5x. 6 distributed to x is 6x. And 6 distributed to 5 is, and I'm actually going to be a little bit clever here because I want everyone to notice something. I'm going to leave it as 6 times 5 rather than the number 30. Because, one last line, I'm going to do a little bit of grouping here. I'm going to take out the GCF of these two terms that have the x in common. Right? Notice that these two expressions here, 5x plus 6x and 5 plus 6x are the same. We have 6 times 5. And now we have a expanded version of x plus 5 times x plus 6. Okay? And this is what's going to allow us to generalize how to factor quadratics. Mrs. Contreras, what do you notice here?
We have a sum and we have a product.
And I'm going to go ahead and write down the final answer, 11x plus 6 times 5, which is 30. All right, if I were to give you x squared plus 11x plus 30, what would you need to think about if you wanted to factor this?
Well, I could think about 11 is what plus what. Right? That's one way I could think about it. But the problem with that is that there's an infinite number of numbers that add up to 11, positive 11. So negative 89? Yeah, 89.
Yeah, you could do like 1 million minus 999,989. Like there's an infinite amount of things that add to 11. I agree. What's a better way to approach this?
Well, there are a finite number of factors of 30, right? Like 30 is only a list of what, like maybe 8 numbers of 30 times 1, 2 times 15, 3 times 10.
I don't know why I'm going small, big,
5
small.
times 6.
That's bothering me. You like chaos. I like order. What did you say? 3 times?
10.
10. And then 4
5 times 6.
5 times 6?
5 times 6.
Cool. All right, yeah, so there's a finite amount of things that multiply to 30, an infinite amount of things that add to 11. So let's ignore this and then look at these. 31, 15, 2, 10, 3, 6, and 5. Right? And then we want to use this 6 and the 5 because those sum to 11. Right? This is why we look for two things that multiply to 30 that add to 11. Right? This is a long-winded discussion on why we do this strategy that many of you may already know. Right? Many of you may look at x squared plus 8x minus 20 and have a routine in your head, but we want to make sure that you know why that is the routine that you're doing. That's the goal this year, is to know why we do certain routines. So let's do it here. And Mrs. Contreras, what are the products? What are the possible products that multiply to 20?
1 and 20, 2 and 10, 4 and 5.
Cool. Now, what do you notice about that 20 though?
It's negative.
It's negative. So
one of them needs to be negative.
Mm-hmm. So one of these needs to be negative. Can you think of, I'm not going to write down the negative because that clutters things up. You like chaos, I don't. So I'm just going to leave it as 1, 20, 2, 10, 4, and 5. And I want to think about, can I add these numbers somehow so that when one of them is positive and one of them is negative, do they add to 8? Do you see which one it is?
I think so. I think it's 2 and 10, as long as you make the 2 the negative one.
Yes, I'm actually going to throw a negative now, as to not clutter everything up, just clutter up the one that needs the negative. 10 and negative 2 sum to 8. Right? So using this strategy from above, x minus 2, x plus 10. Cool. We have factored. We have taken a quadratic and decompose it into the product of smaller expressions. And the last thing I'll say here for this problem is factoring can be really difficult. Right? This problem, maybe you look at it and you've done it before. But factoring, and I promise you, factoring will get difficult quick. But checking your answer is not difficult. Right? That's just the distributive property. So let's just do that real quick. Right? X times x is x squared. And I am going to take, I'm sorry, Mrs. Contreras, but I am going to take advantage of FOIL here. I'm not going to say it, even though I just did.
Oh.
But I am just going to go x times x is x squared. Negative 2 times x is negative 2x. X times 10 is 10x. And negative 2 times 10 is negative 20. And
So you didn't even FOIL there. You switched the interior terms.
Yeah, I FIOL. X squared minus 8x minus 20. That should be a plus 8x, sorry. Yeah, so while it was maybe a little bit silly to do it here because we're just factoring a quadratic with leading coefficient 1, checking your answer is always a possibility if you're nervous about your answer being incorrect. All right, so we will leave these two for you to do. And
it's also okay to be incorrect, right, Mr. Kirk?
It is okay to be incorrect, right? But when you're incorrect, you should be reflecting and trying to discover what you were incorrect about. So the process does not end with being incorrect. The goal is the process will end with being correct, but what happens in between the beginning and the end is anyone's game. All right, so let's keep going. What do we got here? Ooh, special cases.
Wow, they
scroll down a little bit more. Special cases. All right, what
is
makes
it because
this
it's a y? I think it's because there's a y.
It's not because there's a y. The y is there just to establish like the variable could be anything. It could be a smiley face. It could be a banana. It could be a redwood tree, although that would be a really big algebra problem.
It could be an Ewok. It would be a lot smaller.
That was like the worst dad joke I've ever made. All right. It could be an Ewok. All right. Why? That is not what makes this special. What makes this special is its final answer, its final form. So what do you see that's unique about this one?
Well, 25, that's a perfect square.
That's a huge, what I like to, I guess I could call it a purple flag because that's what I'm on. But I throw up a purple flag right there because that is an important observation. We want to look for special numbers because very often they're there for a reason. So we got a special number, 25.
It's also a positive 25.
That's convenient too, because we got a negative 16 over here. All right.
And then, well, 5 and 5, they add up to 10.
Sweet. So I think you just found the two numbers. We got y plus 5 and y plus 5. Sorry if I just made the microphone pop. We got y plus 5 times y plus 5. We have decomposed this. We have factored this. Right? Two smaller expressions that multiply to a larger expression. But something special about this.
They're the same.
They're the same. And what do we do when, we did it earlier in the first problem. What do we do when two things are the same?
Well, we can make them an exponential term instead, which I think in this one, this is more efficient.
Yeah, I agree. This too is way less writing than this if we're talking about real estate. And just like laziness. Efficiency and laziness and everything. Both are correct. There's no real reason why you need to simplify it to a power, but we can do it here, right? And the reason why this one is a special case is because we can do this. And when you can do this, we give it a name. We call it a perfect square trinomial. Right? The perfect square trinomial is this thing, not the final answer, but the original problem is a perfect square trinomial. Tri, meaning there's 3 terms in this expression, and perfect square, meaning when factored, you can write it as the square of a single expression, y plus 5 squared. We call this a perfect square trinomial. Now let's look over here. We have the middle term missing.
It's gone.
What are the factors of 16?
4 and negative 4.
4 and 2 and
negative 8.
Negative 8. Right. This list is going to get really long if I put negatives on 2s and the 8, so I'm just going to get rid of those like I like to do. And I think we're missing 1 and 16.
1 and 16.
Yeah. What do we need to add up to?
0.
0. Do any of these add up to 0?
4 and 4, as long as you negate one of them, those add up to 0.
There you go. So we got x minus 4 and x plus 4. Sweet. All right. So this one is also a special case because we are decomposing into two expressions where they look exactly the same except for that middle sign, plus versus minus, SIGN. We call this a difference. Difference, or is it ANC?
That's good, I think. I think that's right.
It's good enough for our class. Don't tell your English teacher. Difference of squares. Sweet. All right. So what we're looking for when we're looking for difference of squares is, are both of the terms perfect squares? X squared is, x times x is x squared, and 16 is, 4 times 4 is 16. We have a minus sign, so this is a difference of squares. And what we can do is we can, whenever you see a squared minus b squared, you can decompose it into a minus b times a plus b. Right? So we want to look for that pattern, and you'll get practice with this. We want to look for that pattern. We want to look for perfect squared trinomials, and we want to look for difference of squares. All right, keep those on your radar. All right, there are no practice problems, I believe, with that. Cool. All right, I want to do something similar with this problem, right? Like we did at the top of the previous page. I want to reverse distribute, but I want to keep things organized so that we can establish a trick that we can do to factor expressions that don't necessarily have a leading coefficient of 1. Right? Leading coefficient, the coefficient is the number in front of a variable. So let's reverse distribute. Help me out here. We're going to get
3 times 2 times z squared.
Awesome.
And then we get what? Negative 3 times 3 z.
Mm-hmm.
Plus 2 times 5 z. And then minus 3 times 5 z.
Minus 3 times 5. Just 3 times
no,
5.
No z. No z.
No z. No z. No z. Okay. Let's do a little bit of grouping. We got 3 times 2 z squared. We have 3 times 3 plus 2 times 5 z. And we have 3 times 5.
What do we do with that that negative sign in the middle, outside of the parentheses? Because if we do that, then don't we need to make inside the parentheses? Don't we need to make that a negative?
Yeah, let's do that. You know, I'm actually gonna do this. I'm gonna make this positive, and I'm gonna make this negative. Is that fair?
Oh yeah, that'll work too, right?
That works, right?
Mm-hmm.
Cool. So this process for factoring quadratics that the leading term is not 1 is very similar to the process that we just did. We're looking for two numbers that when you multiply them, you get 3. We're looking for, you know, I think the best way to look at this is, let me just move some stuff around. Let's look at this as if we had to expand this. X plus b squared, not squared, ax plus b times cx plus d. Let's expand this real quick. And I'm gonna do it for us. You can check my work when I'm done. We're gonna have acx plus bcx, not bcx, bc plus adx plus bd.
I think the first x needs to be squared.
Thank you. Cool. So this is just going to help me kind of justify what's happening over here. Right? Now, in the previous example, we were looking for two numbers, two of which that multiply to the final term and added to the middle term. Here we're looking for 4 numbers. We're looking for 2 numbers that multiply to the first term, in this case down here 2. We're looking for 2 numbers that multiply to the last term, 10. And those numbers need to be special so that AD plus BC adds up to the middle term. Now, I know this is getting a little bit abstract, but there's a very efficient way to set up all the possibilities so that this process becomes streamlined. So I have AC right here. I am going to write the possible ACs down here. What are all the possibilities that multiply to 2?
Just 1 times 2, because 2 is prime.
Yeah, right? So this is A, and this is going to be C. Right? I'm going to real quick write 2 and 1 because A might be 2 and C might be 1. We have to figure out which one's A and which one's C. What are the possibilities for 10?
1 times 10, 2 times 5, and I think that's it.
I think you're right. Right? I'm going to make this red. A, C, B, D. Right? That is what I want. Cool. So we have possibilities for A, we have possibilities for C, we have possibilities for B, and we have possibilities for D. Now I want to look at what is AD plus BC in all of these situations. Right? And the way I've set this up is just we have to do a little bit of cross multiplication. I'm going to look at A times D and C times B. I'm going to look at 1 times 10 and 2 times 1. Do those sum to -9?
No.
No. And if I were to make this one negative, do those sum to -9?
No.
Okay. What if I were to make this one negative?
No.
No. Okay, cool. So 1 and 2 and 1 and 10 don't work together. It doesn't give us that 9 in the middle. Let's try 2, 1, and 1 and 10. Do you think that's going to work? Can you just do it in your head and figure out if that's going to work?
Well, I wonder because we're aiming for a 9, which is an odd number, and whenever you have an even number times anything, doesn't that still give you an even number?
Yes.
And then even and even is still even.
So if I do the 1 and the 10 and the 2 and the 1, that gives me an even number. Now the 2 and the 10 gives me an even number, and the 1 and the 1 give me an odd number, so that might give me 9. How do you feel about that, though?
I feel like that would be off, though, right? Because like 2 times 10, that's like 20.
Yeah. So we're already getting pretty far away from -9. Let's look at 1 and 2 and 2 and 5.
1 and 2. Well, that's possible.
That's possible. Let's so 1 times 5 is 5. 2 times 2 is 4.
4.
And those look like they're going to get me to -9, right?
Yeah, it's very promising. So we need negatives somewhere, though.
Yeah, it's because we got -9. Can I just put negatives on both? Is that still valid?
I think so.
Right, because -5 times -4 is, sorry, not -5 times -4. Yeah, that's fine. Because a negative and a negative, that's going to give me a positive ultimately.
When you're multiplying.
So which one did we just choose? We chose 1 and 2 and 2 and 5?
I think so.
Right, sweet. So I'm just going to go straight across. 1, 2. So I'm going to have x and a 2. And then 2 and 5. 2x and 5, right? A, B, the original up here, way up here. The original thing was A, B, C, D. So I'm taking A, B, putting them together. C, D, putting them together. All right, so we said we were going to put negatives on both?
I think so, right? Because we need the -9 as what we get from adding up the two BC and AD.
Yep. All right, so we have x minus 2, 2x minus 5. That feels right. Factoring is hard, though, so I'm just going to quickly check my answer. I'm going to expand, 2x squared. We have -5x. We have -4x. And we have +10. And that is going to give me the answer.
Nice.
All right. So we spent a lot of time on these two problems. I want to do one more down here. So we'll do this one together, actually. This actually combines a lot of things that we've talked about so that we can show the efficiency of this technique. Right, there are other techniques for factoring leading coefficients greater than 1, but we want to try to use the most efficient method. So, Mrs. Contreras, what are you thinking here?
Well, I see that there's a common factor of at least there's 2 and x that we can factor out of all the different terms in this trinomial.
So let's go ahead and grab those. So 2x, I believe it's going to be a 6x squared. That's going to be a 7x. It's going to be a minus 5.
And then, well, we know that 6 and negative 5, those are things that we need to deal with for factoring them, right? So we have 6 is what, 2 times 3, 6 and 1. Oh, sorry. Oh, yeah. Okay.
Cool.
And then 5 is just 1 and 5.
All right. Now, I will say, and I'll let everyone at home think about why this is required, but I need to take one of my sets here and flip-flop it. So I need to either go 2, 3, 6, 1, and then 3, 2, 1, 6, or write 1, 5, 5, 1. And I'm going to do the one that requires less writing. And we can talk about this in class, but I do need to flip-flop one of them. All right, so let's start to check. How can we get 7? So we got 2 and 5 is 10, 3 and 1 is 3, 10 and 3. Ooh, I think I just found it right away.
Nice.
That's efficient.
That was efficient.
2x. So we have 2 and 1, 2x and 1. I like to leave out the plus or minus for the end. 3x and 5. And then I think, help me out here, we need a positive 7.
Positive 7, so we need the bigger number, the 2 times 5, to be positive.
Mm-hmm.
And then, so that to get the negative 5, we need a negative on the other.
Yeah, there we go. Boom. We used DCF here, and we also did this factoring greatest common, factoring with a coefficient larger than 1. There you go. That is.
And what if we could just do that in our heads? Like, what if we didn't have to write it down?
That's fine.
Like, do you care?
In my opinion, I think that's totally fine. I mean, ultimately, you're going to be doing so much math that you will develop the skills to do this in your head. But I do want to say that if you need to write it down because I do it every single time. Every single time I write down the factors, and I kind of still do it in my head. I did 2 and 5 and 1 and 3 and got 7 in my head. But writing these down was so important for me. And you can imagine if I gave you like 180x squared minus 43x plus like 60, good luck doing that in your head. It might be beneficial to write things down. All right, but there you have it. And I'm not going to expand this because I'm pretty darn confident. But if it is wrong, then everyone can yell at me in class. And you can laugh at me in Mrs. Contreras' class. There you go. Okay, that is the factoring basics. And we will get lots of practice in class. Nice. Any last minute thoughts?
I think we need a cool closeout.
We do.
Okay,
don't forget to like and subscribe. Smash that like button. Smash that subscribe. We'll think on this. This is the most important thing that we have to deal with right now.
Yes.
How do we sign off these videos?
Absolutely.
Hopefully that wasn't too long. I wasn't watching the time.
I wasn't either. I think it was like half an hour though.
I'm okay with half an hour. I hope.
Oh, okay. Yeah. Right on.
If it's like an hour, I'll be like, oh my gosh.
We can double speed it, and then it's half an hour.
That's true. It's going to be on YouTube. Everyone, if you're still here and you're still watching, which you should be because it's going to be in Canvas, you double speed that thing. Double speed it. Go to the little gear in the bottom corner, go up to playback speed, and click ×2. I'm a 1.75 person myself, but if you can comprehend at 2 times speed, good luck.
I like double speed.
All right.
I feel like that's how I talk normally. It's double speed.